Video goes through the concepts of complicated versus complex problems and causality as well, in particular linear versus nonlinear causality that are specific conceptualizations in complex systems and very important conceptualizations in complex systems. And these conceptualizations are taken from a book that I highly recommend by Peter Hovmand, 2014, and it's called Community-Based System Dynamics. So what are complicated versus complex problems? So complicated problems are really difficult problems. So Hovmand or Peter Hovmand define complicated or perceives complicated problems as difficult problems because they involve a lot of moving components or elements and details, versus complex problems in society in general. They are considered complex because they involve lots of possible interactions and explanatory pathways. So we normally respond to complex issues by trying to reduce them into smaller parts or smaller elements or components and explore more detailed complexity. So this is usually done by creating categories and jargon. However, lots of detail may ultimately add very little to how we understand an issue. This is what Peter Hovmand argues. So complex system issues really have got properties. And these properties make them hard to understand because of the emergent behaviors of these components that interact within a system. So when they say, for example, a very, very famous saying of the sum of the whole is greater than the sum of its parts, what does that mean, really, when it comes to complex systems thinking? It means that a system behaves in ways that could not be predicted, or it cannot be reduced to characteristics of the individual components or parts. So in other words, the behavior of a system emerges from the interactions of different elements. But these interactions are determined by the structure of the system. And because of that, the structure determines that behavior. So this really needs a shift in the way that we think about problems in general. Now, we come to linear causality versus nonlinear causality. And this is, again, these are very important concepts when it comes to complex systems thinking. So Peter Hovmand defines linear causality is about understanding a system by understanding its component parts and then inferring what a system will do. So in this situation, the focus becomes on the strength of association between causes and effects. So for example, when we increase, which is an example that I am showing on the presentation on this slide, is that when we increase fishing, when we shorten commuting times, this will ultimately reduce traffic and so on. And then also another example to use is that when we increase fishing, this will ultimately increase revenue. So in such understanding, the effects that matter become those that are very close to the causes. So the closer the cause is to the effect, the stronger the effect. And the further one moves from the original cause, the weaker the effect becomes until we distinguish it from a random, kind of disturbance. So in such situations, the consequences of long causal chains get to be ignored, and what determines behavior becomes the strength of the association. Now we come to nonlinear causality. What does that mean? Structure determines behavior in nonlinear causality. And this is very different from linear causality between cause and effect. For example, there are reinforcing feedback loops that explains why the system behaves the way it does. So in here, effects kind of accumulate, if you like, as they move around the feedback loops. To give you an example, again illustrated on this slide, More fish caught leads to fewer fish, which makes it more difficult to catch fish, which leads to fewer fish being caught. So in these situations, what becomes important is not the actual harvest rates of the fish, but how positive and embedded within a feedback loop it is. So it also means that changes in the strength of association will generally have little impact on the system behavior itself, whereas a change in the structure of the system itself will ultimately lead to impact on the system behavior. But we also have to keep a few things in mind, that one of the consequences of structure determines behavior, that way of thinking, is that the structure can create different types of behaviors. So reinforcing feedback loops that produce exponential growth can also produce exponential decline. The one system can produce different system behaviors. So this concept is Hovmand calls dynamic complexity. This view or notion is different from when we think systems are complicated or hard to understand, because they have many different elements, or detailed complexity, as he calls it. Dynamic complexity is concerned with understanding dynamic complexity rather than the fact that the number of components and connections in a system are overwhelming in its detail complexity. So what are the implications of a dynamic complex system? The same basic structure that creates desirable behaviors during one time period can also drive undesirable behaviors in another time. So the feedback here, we come back to the feedback loop. The feedback mechanisms that can drive success in one area can be the same feedback mechanisms that also lead to conflict. This is because situation may be changing. What was once the source of success is now driving failure. So we need to really, it's crucial to understand the structure of a system to be able to identify possible strategies for improving that system. And because of that, framing the issue as dynamic at first, one that involves one or more variables changing over time, is really crucial, becomes when we have these dynamic complexities going on.